Namaste everyone. Welcome to second PUC physics class. So we are almost completing one part, that is the second part of the physics. So we are in the last chapter, that is semiconductors, right? Yeah. So namaste everyone. Welcome to the physics class. Hope you are doing well. So we are in the second part, last chapter, that is semiconductors, which is a very easy chapter. But very interesting also, very developed part of the science, that is semiconductors. Nowadays you have semiconductor devices everywhere, maybe ICs, integrated circuits, maybe any microprocessors, and any circuit nowadays is made up of silicon and semiconductors. So in the olden days we had computers as large as a room. People used to go inside the computer and operate it, because all the devices were of larger size. We were not able to accommodate everything within a smaller size. So at that time, for amplification of the small signals, because a signal may be very weak, a signal in the sense an electrical signal which contains some information, maybe a very weak and its amplitude may be small. If it has to be amplified, we would use some devices called amplifiers. So that needs some devices, some small components to amplify, which have the amplifying character. Amplifying character in the sense, suppose you give some input, it should amplify the same input and give it in the magnified form using some other energy. So transistors nowadays do that. But in the olden days, it was done by some instrument called vacuum tubes. Vacuum tubes used to amplify are used as they were used as amplifiers and oscillators. They are the major parts in computers. So the size of an vacuum tube valves, what you call valves, they were of larger size, something like this, the size of this remote. So like this, even larger than this. So such many valves were used in computers, vacuum tubes. But later the development of science and development of semiconductors made a revolutionary change, and later we started using what are called transistors. Transistors are of smaller in size. I will show it in later classes. It will be as small as one small piece of this chalk. Transistor is very small, and it started using a lesser amount of power and consumed a small amount of space, so everything got miniaturized. So we got computers and all. But nowadays we have the whole circuit containing transistors, diodes, resistors, capacitors, everything put in a small shell, put in a small chip, silicon chip, and that is called integrated circuit, IC. Integrated circuit is a miniaturized form of the huge circuit. All the components are put together and developed in a small IC, that is called integrated circuit, small silicon chip. So again it got miniaturized. Now you can have a pocket calculator, pocket computer, very small sized. So as the science developed, vacuum tubes were replaced by transistors. Transistors, resistors, and all diodes, all the electronic equipments, that is semiconductor devices, have been put in a small chip called integrated circuit. Now we have thousands and millions of components in a small spaced chip, and you can see it in processor chips and all. So chip means it is a small semiconductor device where the whole circuit itself is developed within it using different techniques. Okay, now the use of semiconductors in the technology field has made a tremendous change. Everything has been miniaturized, and the use of power has been decreased because they consume less amount of power. The speed of operation has been increased. They do the work in a lesser amount of time. So these are all the contributions of semiconductors. Now first of all, what are semiconductors? Why do they have so much of importance in our technological field? Semiconductors are the materials which have the property between conductors and conductors and insulators. What is a conductor? Usually when we say a conductor, we mean the conduction of electricity, whether it allows the charges to flow through, whether it allows the current to flow through or not. If it contains plenty of free electrons, definitely a material will allow the current to flow through. So copper is a good conductor, silver is the best conductor, and iron is a conductor. See, aluminum is a conductor and silver is the best conductor, I told, and they all allow the charges to flow through. They have plenty of free electrons within them. So if you apply a potential difference across a aluminum rod or a silver rod across this, if you connect a battery, charges flow. Charges flow easily across this, maybe electrons or something else. They are all conductors, and conductors need not be in only solid form. You can have some electrolytic solutions also, like a copper sulfate solution. It allows the charges to flow. So it contains ions, right? So charge flow means it need not be only electrons. It may be positive ions also, negative ions also. It may be some holes also. In semiconductors you will get holes which are positive charges. So how do you conclude here now? So conductors are the materials which allow the charges to flow through, whose resistance is very less. Resistance to the flow of charges is very, very less. They show very less resistance. And their resistivity, what do you mean by resistivity? Resistivity means if you take a material of 1 meter length and 1 meter square area of cross section, area 1 meter square, area of cross section like this, and length 1 meter, if you take such a material, how much resistance it gives, that is called resistivity. Resistivity is the resistance given by the material of unit length and unit area of cross section. That is resistivity. Resistivity of conductors is very, very less, and it is of the order of 10 to the power minus 2 to 10 to the power minus 6 ohm meter. So conductors show very less resistivity, 10 to the power minus 2 to 10 to the power minus 6 ohm meter. Ohm meter means it is per unit length per unit area of cross section. You will come to know why this unit, ohm meter. So conductors have very less resistivity. They are very good conductors of electricity. They allow the charges to flow through very easily. They conduct electricity. What about insulators? Insulators are the materials which do not allow the charges to flow through, because they don't have free electrons at all. They have electrons, all the electrons are bound and they are tightly bound inside, revolving around the nucleus, and they are not free. The bond between the electron revolving around the nucleus and the nucleus is very strong. But they are not found inside the nucleus, they are outside, always they are outside, but they are not free. They are very tightly bound. So if you call an electron in an insulator like wood, dry wood I am talking about, not the live wood, because it is having some water content. Dry wood is a good insulator, glass is a good insulator, and plastic is a good insulator. If you ask any electron from glass or wood, can you carry current? Can you flow in a particular direction? No. I have a particular job. I have to revolve around the nucleus. I have to form the bond between the atoms. They are not free. So there are no free electrons in an insulator. They give high resistance to the flow of current. So if you connect a battery across a plastic rod, no current flows, because there are no charge carriers inside, free charge carriers inside. So insulators show very high resistance of the order of 10 to the power 11 to 10 to the power 19 ohm meter. Their resistance is very, very high. Here comes materials which are called semiconductors. Semiconductors are the materials. So here you can write glass, cotton, plastic, or things like dry wood and all. They are all insulators. And here you can write copper, silver and all. Semiconductors are the materials which have their conducting property between conductors and insulators. They are neither very good conductors, but at the same time they are not insulators. And they are called semiconductors. They have their conducting property between 10 to the power here minus 2 to minus 6, 11 to 19, 10 to the power minus 5 to 10 to the power plus 6 ohm meter. They have a little bit of some resistance. Now why they are neither very good conductors nor very good insulators also? They don't completely block the current to flow through, and they allow to some extent they allow the current to flow through. We will see why it is so. That is because of their structure. So semiconductors are the materials which have the conducting property between whose conductivity or resistivity lies between that of conductors and insulators. Now you remember, resistivity is the reciprocal of conductivity. 1 by conductivity is resistivity. Conductivity means how much does it allow the current to flow through. Exact definitions and all you will study that. So reciprocal of conductivity is resistivity. Now resistivity is less means it is a good conductor. Opposition is less. Resistivity is more, plus 11, plus 19. It is a very good insulator. It doesn't allow. It fairly larger, neither very small nor very large. It is 10 to the power minus 5 to 10 to the power 6 ohm meter. That is semiconductors. Now this semiconductor electronics is the branch where we study the controlled motion of these charges. Semiconductors play an important role because you can control the amount of charges, free charge carriers. What you can do is, semiconductors show some particular characteristics. They can receive some external impurities. They can receive some other dopant atoms, thereby changing the number of free electrons in them. So you can control the amount of free charges, you can control the current. So this controlled motion of free charges is called semiconductor electronics. Right? In semiconductor electronics, we study about the controlled motion of the charges. If you want a particular current to flow through, you can control it by controlling the number of free charge carriers. If you want a very high current to flow through, you can increase the charge carriers and you can do so. And these are all done by a process called doping. You can't dope an insulator so easily. It doesn't satisfy we can't satisfy the conditions of insulator. You can produce some free electrons in the insulator by adding some impurities into that. Not possible. Even in conductors, it is not possible to decrease its resistance. It is already having in conductors you can't increase the resistance. It is not so easy. Whereas here you can control. So this controlled motion of charges is done in semiconductor electronics, semiconductor devices. Okay. Now, now if you want to differentiate conductors, semiconductors and insulators, you have to see another theory called band theory. What is band theory? Band theory. Energy band. We have seen in atoms, right? Atom chapter that energy levels or energies are distributed to the electron. Suppose in an atom, for example in hydrogen, if you call 2 electrons from 2 atoms and ask them, how much is your energy, how much is your energy? Electrons in the same atom or in same material or same atom may not have the same energy. Some electrons will have more energy, some electrons will have less energy. So some electrons will be in the innermost shell, some electrons will be in the outer shell. So they will be distributed in different shells, right? See, different energy levels. So if you just go on studying about the energy levels of electrons, then you will find that electrons will have a particular energy level. If you give energy to certain electron, it will just absorb a particular energy and it goes to the group of another group of electrons or another energy level. And if the energy supplied is not enough to go to the next energy level, it simply rejects it and it doesn't absorb it at all. So that is what you call quantum nature of energy. Energy is absorbed or given out in only the form of quantas, that is packets of energy. So if an electron absorbs energy, only if it is enough to go to this energy level, it absorbs. Otherwise it simply rejects it and it doesn't absorb it at all. If that energy is absorbed and if it is enough to go to the next energy level here, then it comes here and this is an unstable state. Electron doesn't remain there for a long time. Very soon it comes back within 10 to the power 8 minus 8 or 10 to the power minus 9 seconds. When it comes back, that energy is emitted in the form of light, heat or anything and some electromagnetic radiation. Now, this energy level, as you go to the higher and higher energy levels, you will find that these energy levels are closely packed. The difference between this energy level and this energy level will be very less as you go to the higher energy levels. So at the outermost energy levels, the energies are so closely packed that such that they appear to be continuous. And also in solids, maybe conductor, insulator or semiconductor, in solids, and especially I am talking about semiconductors now. In solids, the atoms are closely, tightly packed. So energy level of one electron and another electron may be overlapping. So when the energy levels overlap, after certain stage, you will find that the energy levels are almost continuous. These continuous energy levels, of course, there is a difference between one energy level and another energy level, but still they appear to be very continuous since they are very close. Energy values are very, very close. So if you try to differentiate all the electrons having minus 13 points electron volt energy come here, then you will find few electrons. All the electrons which are having energy of minus 3.4 come here, minus 1.51 come here, and later on finally what happens is the energy levels become so and so and so closer that you can't have two numbers or two energy levels different. Then you can have all the electrons having energies greater than 0.51 electron volt, make a group, because it is continuous, right? You can, as if we have first rank 600 and 596 first rank, okay. First rank come here, second rank 595 come here, and when you go to the lower marks, what happens is, there are many people who have scored 580. There are plenty of people who have scored 570. And there is a huge crowd of students who have scored 500. And if you go to 400, 300, there may be many, many numbers. So what you can do? Can you differentiate them? Now, who is the person who has scored 436? There are so many people. So what you can do? You can make them a group. It is a group of people who have scored between such and such a mark. Similarly, here, after certain energy level, the energy levels are continuous, and now we don't differentiate between the two small different energy levels. We continuously make them a band. So set of energy levels which are continuous is called a band. So closely packed energy levels in solids which have a small energy difference and which appear to be continuous, they are called energy bands. So if you have such bands, a group of students who have scored 436, a group of students who have scored first class, group of students who have scored second class, like this, that is a huge number, because you can't have a one by one identity as if you had in first rank, second rank, because the people who have scored above 590 and 600, that may be less. So you can have individual attention, that this is the person who has scored 596, this is the person who has scored 595. There are only one or two persons. But when you go below certain value, it is continuous. So that is called energy band. Now, if you go on searching that energy band, you will reach energy band where there are electrons. There are electrons which possess that energy, which is the highest energy band which is occupied by an electron. So if you go on searching whether there are electrons with this energy, whether there are electrons with this energy, whether there are electrons with this energy, sir, this is a group of electrons which have particularly this energy. And how much energy they have? Sir, this much, sir. And if you go beyond that energy level, don't you get any electron? No, sir. Then that energy band which is filled with electrons, or if any electron is having a particular energy, then that band is called valence band. Valence band is the highest energy band which contains electrons, right? There should be at least one or two electrons which possess that energy. Then it is called valence band. So highest filled energy band is called valence band. So if I put the energy level diagram like this, this is valence band. Highest filled energy band is called valence band. And if you see another band which is not filled, then it is called conduction band. The energy band above the valence band which is not filled is called conduction band. So I will come back now. You know what is band? Band is the set of energy levels, continuous energy levels, which can be collected together and which can be called as one band, called by the name one band. So valence band is the highest energy band which is filled with electrons. Now if you come to the lower energy levels, sir, is there any electron with this energy? Definitely. In that atom there are electrons with this energy. Is there any electron with this energy? Yes, there are electrons with this much of energy. Is there any electron with this much of energy? There is. Either one, at least one, there is one electron or more than one electron with this much of energy. Then it is valence band. Is there an electron with this much of energy? No. This is a collection of energy levels. See the different energy levels. You make an announcement in the atom saying that electrons with this much of energy come here, no electron. That means it is conduction band. Electrons or the energy band just above the valence band is called conduction band. Surprisingly, you will find that there are no energies between these two. Between these, there is no energy level at all. You know that electron cannot revolve around in all the orbits, right? There are certain conditions. There are certain orbits called the stationary orbits where only you can find out electrons, and you can't find electrons anywhere else. That quantum number, angular momentum must be equal to nh by 2 pi. So certain conditions has to be satisfied. So you can assign some energies here, but there are no electrons which are found which can absorb that energy. Electrons can absorb energy and may revolve around the nucleus in a particular orbit where the angular momentum must be equal to nh by 2 pi. And this energy gap, or this gap where there are no energy, no electrons are found, that is called energy gap. Sir, here there are no electrons here, right? Then why can't you add this to energy gap? No, not like that. If an electron is in the valence band, if it absorbs energy, then it can attain any energy of this. Electrons can go to the conduction band, but may not be found here. We will see when it will be found. There may be electrons in the conduction band. So I am talking about now the case where there is no extra heat energy or nothing. When no extra energy is available, electrons will be found in the valence band. That means I call it as 0 Kelvin. Okay, this is not okay, this is 0 Kelvin. Okay, this is not okay. If you call this as okay, then it is not okay. It is 0 Kelvin, right? At 0 Kelvin, energy levels in the valence band are filled. At least some energy levels. That means you can find some electrons which have this energy. Of course, say I will call this as energy in electron volt, right? Some value. And simply x-axis has nothing. Okay. You can find electrons with this much of energy. There are electrons found. But at 0 Kelvin, there are no electrons with this much of energy. Why, sir? Because there is no external energy, there is no heat energy, so all the electrons are here. But at room temperature, there is enough amount of heat energy available. Electrons may absorb that external heat energy, and they may go to this conduction band by absorbing at least this much of energy, what is called energy gap. So how do you define energy gap? So you have defined valence band, the highest energy band which is filled, and of course the energy band below this are also filled, but we don't call it as valence band. The highest energy band which is filled is called valence band, and the band, energy band, which is very next to the valence band is called conduction band. This contains some energy levels, and the energy difference between top of the valence band and bottom of the conduction band, this gap is called energy gap. Energy difference between the top of the valence band and bottom of the conduction band, because you know band is not a single energy level, it is a collection of many energy levels, right? So energy level of this is less, energy level of this is more. Similarly, this is less, this is more. So energy increases as you go above the y-axis. Now, so what is the actual energy gap? It is the energy difference between the bottom of the conduction band and top of the valence band. That energy difference is called energy gap. Why it is called energy gap? Because no electron can absorb an energy which is, or possess an energy which is in between these two. No electron can possess, because it doesn't satisfy the conditions. And in reality it is not possible for the electron to satisfy here. For example, are there any people in the first floor? Yes. Are there any people on the top floor? No. Because usually nobody will go to the top of the building, right? They will be either in the first floor, second floor, third floor. They don't go to the top of the building. Suppose there is some particular work, like for a plumber or an electrician or a person who is connected with some computer works, and if he wants to draw somewhere, they will go to the ceiling, right? They will go to the top of the building, and nobody else will go. So are there any people on the first floor? Yes. Second floor? Yes. Third floor? Yes. What about between first floor and third floor? Nobody will be there, right? Is there anybody between third floor and fourth floor walking around? Not possible. because either you should be in the third floor or in the fourth floor. You are not supposed to be walking somewhere in between. If you are walking somewhere in between third floor and fourth floor, we doubt whether you are a human being or not, somebody else, and that's a doubtful case. It is not possible. So either you can have here energy or here energy. In between it is not possible, because we have our own conditions. We will walk only when there is a support to us. If there is something giving reaction, a floor, without floor we can't walk. There should be a support from reaction giving object. So that is the thing. Similarly here, electrons cannot absorb energy which is found between these two. So that is why it is energy gap. So energy gap is the difference in energy of the bottom of the conduction band and top of the valence band. Valence band is the highest energy band which is filled, and another energy band which is above the valence band is called conduction band. Well and good. Now this is found in solids. Now how do you differentiate conductors, semiconductors and insulators on the basis of band theory, this band? Now in conductors, so this may be a good idea for you. If you know this clearly, then you can proceed. If it is a insulator, how the electrons, and because these charge carriers are mainly electrons, right? There may be ions in electrolytic solution, there may be ions in discharge tubes. In tube lights it is ions which are flowing from one end to the other, and there may be electrons also. Now my question is, what is the situation in insulators? In insulators like plastic, glass, etc., the energy gap is very, very high. It is more than 3 electron volts. So this energy gap is greater than 3 electron volt. There are electrons in the valence band, there are no electrons in the conduction band. No free charge carriers. Sir, when is this the situation? Always. Whether it is at room temperature, whether it is at 0 Kelvin, at any time, even if you supply some external heat energy so that electrons will absorb the heat energy and go to the conduction band, that is your expectation, but they don't go because this energy gap is very large. So an insulator is a type of material where conduction band and valence band are separated by a very large energy gap. And even if you supply an external heat energy, electrons don't go to the conduction band, because this much of energy, when you start supplying in the form of heat, what happens is it may lead to some other problems, and so much of heat energy will create some other chemical changes, and you can't produce free electrons by making them to go to the conduction band. And another thing you have to remember is, if you are successful in any material, if you are successful in putting an electron from the valence band to the conduction band, then the thing is, those electrons become free. Once they are here, they become free, and they are now ready to conduct. They say, sir, we are free, give us some work, apply a potential difference and we will move. They are free electrons. They are not taking part in any of the bond. They are not bound to the nucleus so tightly, so they can move freely here and there, and they can conduct electricity. So, but in insulators, you can't produce such free electrons in any manner, even by supplying energy in the form of light or heat or any source. Anyway, electrons can't go to the conduction band. So in an insulator, conduction band and valence band are separated by a very large energy gap. So electrons can't move to the conduction band at all. Insulator remains as insulator at 0 Kelvin as well as at room temperature. Remember this energy gap. Now what about the conductors? Why conductors are very good conductors? That's why they are called conductors, right? They are very good conductors, they conduct electricity, they have plenty of free electrons, because this energy gap is very less and may be even 0. They may be overlapping. In a conductor like silver or copper, the conduction band and the valence band overlap like this. This is conduction band, sorry, that is valence band. This is valence band and conduction band overlap. The energy gap will be almost 0. And if there is an energy gap in some conductor, it is very less. So in a conductor, conduction band and valence band are separated by a very, very small energy gap, and it is almost 0 electron volt. They overlap sometimes, so that electrons, of course, at 0 Kelvin they may be found in only valence band. But a small supply of energy, if you bring this conductor from 0 Kelvin to the room temperature, suddenly it becomes a very good conductor. Reason is, a small heat energy will be enough to lift them from valence band to conduction band, because there is no energy gap at all. A small push is enough. Suppose a ball is found in a ground, just a push is enough, it starts moving, right? In the same way, but it is not like that here. Simply I have given an example. Here, a small energy supply is enough, just a small energy. Electrons can go to the conduction band, and that conductor becomes a very good conductor of electricity. So all conductors, copper, aluminium, silver, iron, they are very good conductors of electricity at room temperature, because by using heat energy, almost all the electrons go to the conduction band. They become very free electrons. So there are plenty of free electrons. Now, so if you observe, in an insulator, valence band is filled completely or partially, we don't know. That depends on the material. It may be filled with electrons. It contains, valence band contains electrons. What about conduction band? In conduction band, there are no electrons. That means there are no electrons with the energy of this much. That is the meaning, right? There, in the material, there are no electrons with the energy this much, conduction band. When? Even at 0 Kelvin, even at room temperature. Even if you heat it separately, even if you supply heat energy and try to heat it, no electron can go to the conduction band. So in an insulator, valence band is filled with electrons, partially or completely, but conduction band is always empty. That's why it is never a conductor. It will always be an insulator. What about in a conductor? In a conductor, the conduction band and valence band are separated by a very small energy gap. So at room temperature, a small energy that is available is enough, and that electrons will go to the conduction band, and it becomes a very good conductor. So in a conductor at room temperature, valence band is filled, conduction band is also filled. At room temperature, in an insulator, valence band is filled, conduction band is not filled with electrons. Now we will go to semiconductor. Hope you can see this here, or somewhere I have to write it here. What are semiconductors? Can you see this? I will write it here only, okay? I'll write it here only. Semiconductors. What are semiconductors? In semiconductors, we have an energy gap between conduction band and valence band. Suppose this is conduction band and this is the valence band. See, in the hydrogen atom model, in the atoms, we have studied one by one energy level, right? Ground energy level, that is ground state, with minus 13.6 electron volt. Next energy level, they are all separate energy levels, but as you go away, they become continuous. This is a set of energy levels, that is called valence band. In a semiconductor, at 0 Kelvin, you know it, at 0 Kelvin, valence band is filled, conduction band is empty. Sir, it is very similar to this. Yes. At 0 Kelvin, semiconductor is a best insulator. It is as same as an insulator, because there are no free electrons in conduction band, and there are no free electrons at all. So at 0 Kelvin, semiconductor is an insulator. Remember, because there is no external heat energy available, and electrons can't gain energy, they can't go to the conduction band. What about the energy gap? It is lesser than 3 electron volt. In semiconductors, energy gap is lesser than 3 electron volt. So if the energy gap is lesser than 3 electron volt, then it is a semiconductor. If it is greater than 3 electron volt, it is an insulator. Of course, in conductors there is no energy gap at all. They overlap. But still they need a small amount of energy to go to the conduction band. So only at room temperature they will conduct. Now semiconductors, empty conduction band and filled valence band, but energy gap is less. So when you bring a semiconductor from that 0 Kelvin, where it is a perfect insulator, to the room temperature, now heat energy is available, because at room temperature heat energy is available. When heat energy is sufficient to lift the electrons, because energy gap is less, electrons can go to the conduction band. Now it starts conducting. But remember, by supplying heat energy, that is at room temperature, by absorbing the heat energy, the number of electrons that can go to the conduction band is not as large as a conductor. I have rubbed it. In a conductor at room temperature, small energy is enough, plenty of electrons go to the conduction band. It acts like a very good conductor. But in a semiconductor, it cannot happen so. Electrons can go to the conduction band, but not in large number. That's why it is called semiconductor, because it can neither act like a very good conductor. At the same time, it is not an insulator. It is a partial conductor. It contains some fairly good amount of electrons, free electrons, but not as much as a conductor. So, in a semiconductor, if the energy gap, since the energy gap is less, at room temperature, some of the electrons can absorb energy and can go to the conduction band. So, at 0 Kelvin, valence band is filled, conduction band is empty. But above 0 Kelvin, at room temperature, conduction band and valence band are both filled. May not be completely, but they may be filled. So it acts like a conductor now. So I have told semiconductor devices are constructed and the flow of charges is controlled. The controlled motion of electrons, that is what is done in electronics, right? Semiconductor electronics. Now how do you do that, sir? Do you supply heat energy as you like and lift the electrons into the conduction band and make them free and make them conducting electrons and make it a good conductor? Is it so? No. But this is only property. You can't have many free electrons you can't produce many free electrons by supplying heat energy and making the electrons go to the conduction band. That process is a very bad process. You can't achieve your goal and you have to go for something else. These semiconductors, they have another property of receiving some impurities from outside. And you have to study the atomicity, that how many valence electrons are there and how they are forming the bond, what type of bond and all. So this is the story of conductors, semiconductors and insulators. So very important difference between them. Maybe a question for final exam also. Distinguish conductors, semiconductors and insulators on the basis of band theory. And or simply write what are the differences. Conductors are the materials which conduct electricity, and insulators which do not conduct electricity. Semiconductors have conducting property between conductors and insulators. And what else? In conductors, the resistivity is, so conductors have very low resistivity, 10 to the power minus 2 to 10 to the power minus 6. Minus 8 actually. What did I write actually for conductors? 10 to the power minus 2 to 10 to the power minus 8 ohm meter. And for semiconductors it is from 10 to the power minus 5 to 10 to the power 6 ohm meter. And for these insulators it is up to 10 to the power 11 ohm meter to 10 to the power plus 19 ohm. It is very high resistance. The resistance per unit length per unit area of cross section, that is called resistivity. So resistivity is, suppose you forget the numbers, simply write like this. Resistivity is very low for semiconductors, conductors. For good conductors, resistivity is low, opposition is less, because there are plenty of free charge carriers. For semiconductors, resistivity is neither very large nor very low. For insulators, resistivity is very high. Okay, or you can use the numbers minus 2 to minus 8 for conductors, very less. Resistivity 10 to the power 5, 10 to the power minus 5 to 10 to the power plus 6 to semiconductors, 10 to the power 11 to 10 to the power 19 ohm meter to insulators. Okay, and the energy gap. In insulators, the energy gap is greater than 3 electron volt, and in conductors they overlap, there is no energy gap at all, and in semiconductors the energy gap is less than 3 electron volt. In conductors that valence band is filled and conduction band is also filled at room temperature, whereas in insulators conduction band is always empty, valence band is filled, but in semiconductors at 0 Kelvin conduction band is empty, it is a perfect insulator, and valence band is filled, but at room temperature, since heat energy is available, electrons may absorb heat energy and can go to the conduction band, and that leads to the conduction of the material. So conduction band may be filled at room temperature, and valence band is also filled, but at 0 Kelvin, very similar to insulator. Okay, so that is the thing. And now what happens here? One more thing. See, we have different types of charge carriers. If you observe a metal and apply a battery to the two ends of a metal, say this is a silver rod, connect a battery, then electrons in the silver rod will drift like this, they will move. That produces current. Of course, current is in this direction because current is opposite to the flow of charges. Now, right, what are the charge carriers in metals? It is the free electrons. Sir, do you have any positive charges moving inside a metal? No, because protons which carry positive charge are inside the nucleus. It is very difficult to remove the protons because in such a electric field, by applying a potential difference and a battery, you can't remove protons. It is not at all possible. And you know, with what energy is needed to break a nucleus and all. So it is not possible. It is not protons, only electrons. Sir, what about in a discharge tube? You have seen a tube light? In a tube light, what happens is, it is a vacuum tube, right? Or it is a tube filled with the gases at low pressure. You have different colored tube lights usually, and you can have that. Suppose you might have seen some these shops in big cities. The name of the shop will be written in the form of tubes, right? That glowing tube, and that will be of different colors depending on the gas filled inside. So gas at low pressure will be filled in this, and here will be a coil, and that coil emits electrons. These electrons move inside that gas. They collide with the gas atoms. It's the same way in which we did hydrogen spectrum, right? If this is filled with hydrogen atoms get collided with these electrons. So those atoms give that energy in the form of light. That's what happens. Now, that is the principle of tube light. Now, when these electrons move, they collide with the atoms. Atoms lose energy, lose some electrons. They get converted into ions. So, ions and electrons, both are responsible for the flow of charges in a discharge tube. We call it as discharge tube. Discharge means discharge of electrons. Electrons which are within a filament, when that filament is heated using electricity, that filament getting heated gives away electrons. So electrical energy is converted into heat energy. Because of heat energy, electrons come out. When these electrons are accelerated, they collide with the atoms, and atoms release some electrons. So you have plenty of electrons and positive ions. Electrons and positive ions are the charge carriers in discharge tubes. We have a electrolytic solution like copper sulfate, right, like this, for example. If you dip 2 copper ions and connect a battery to this, you know that some positive ions get deposited in one plate, negative ions get deposited in the another plate. You know, copper ions, positive ions, sulfate ions or negative ions, they get deposited. So there is a current. If you connect an ammeter, you can get the current in the copper sulfate solution. Current flows. Which are the charge carriers in copper sulfate solution or electrolytic solution? We call it as an electrolyte. Both positive and negative ions. Positive and negative ions are the charge carriers in this electrolytic solution. Sir, what about? So conductors, free electrons, and discharge tubes, these ions, positive ions and electrons. Here positive and negative ions. What about in a semiconductor? Electrons as well as some positive charges called holes. What are holes? Now one electron, when it goes to the conduction band, what happens is this electron has left this place now. So here we have a vacancy, that is called hole. Holes are found in the valence band. Free electrons are found in the conduction band. Remember, if electrons are found in the valence band, they are bound electrons. They can't move. They are not the charge carriers. They are charges. They are negative charges, but not carriers. They can't move from one place to another. They will keep on doing their job and they remain at the same place. Of course, they can't move from atom to atom. inside the material. They can't move. So they are not charge carriers. But if this electron goes to the conduction band, now it is free from all the bonds, it is free from all the restrictions, so it can move freely. Now it is a free electron. Whereas when an electron becomes free in a semiconductor, when it goes to the conduction band, it leaves a vacancy. A bond is left vacant because this was the electron which was forming some bond. Now that bond is kept vacant. Now what the other electrons do? Other electrons go and fill this bond. Now when they go and fill this bond, they are leaving a bond here. That positive charge or that hole or that vacancy is shifted here. So we will see it in detail how it is so. In a semiconductor, electrons as well as holes both are responsible for the flow of charges, flow of current. So if you are asked, this is an important question. If you are asked to write what are the free charge carriers in conductors, electrons, discharge tubes, electrons and positive ions, electrolytic solutions, positive and negative ions, semiconductors, holes and electrons. What are holes? Absence of an electron is called hole. What is the charge? Positive. It is not a proton. We will see what is actually a hole and we will carry it on. So thanks for watching my class. In next class we will go with more theory and we will have it and we will go deep into the devices like diodes and all. So thanks for watching my class. Keep reading this one because this contains more amount of theory but very good questions for entrance exam. Very easy questions also. Don't waste the time and take care of your health. Thanks for watching my class. Thank you.